Okay, so we are now starting a new chapter on solution thermodynamics and colligative properties. Materials in this chapter would require you to remember some of the previous concepts we talked about, particularly in thermodynamics, the concept of free energy, concept of entropy and enthalpy. And the idea here is we want to start in the first half of the chapter to explain how solutions form. So when you mix two things together, a solid and a solvent, how do we predict whether those two components will mix or not? So let's take a look at the thermodynamics of solution formation, or the energetics of solution formation, right? How can we use free energy to help explain whether a solution forms or not? As a quick reminder, we have two components in a solution. We have our solvent and we have our solute, right? And the solvent is, of course, the component that exists in a higher concentration or higher proportion, and solute is the one that exists in a smaller proportion. Typically, in this chapter, we would discuss aqueous solution, although it's not necessarily limited to that. So you could have your solvent being, let's say, acetone or alcohol or some other organic solvent, but a lot of the concepts that we'll discuss will center on the idea that the solvent is water. The solute could be anything. Could be ionic, could be covalent. We'll discuss both of them. Now, whether or not you will get a solution to form really depends on the free energy of the solution, or what we call delta G of the solution. If we can calculate that number, and we can, we'll do that in a sec, and find the value of the delta G of solution, we can then interpret whether a solution will form or not. And simply the way we do that is just by looking at the value of the delta G of solution. If the delta G of solution is negative, then solution should form spontaneously, just as we predict for any process that has a negative delta G. If the delta G of the solution formation is positive, then the solution formation is non-spontaneous, which means it's not going to form. So if you look at the picture on the right, this picture right here will be when your delta G of the solution is negative, and then this one right here will be when your delta G of solution is positive. Now the question then becomes, how do we calculate the delta G of solution? What reaction should we focus on that corresponds to a reaction where a solution is formed? Well, since we're talking about aqueous solution specifically, the reaction itself is just going to be the two that's shown here. If you have an ionic solute, then you will start with your solute in a solid state, and then it would go into an aqueous state. But what we remember about ionic solutes is that when they're dissolved in water, they split apart into their respective ions. So in fact, what you'll have is this. So in other words, when you're trying to calculate your delta G, your product would look something like this. Sometimes it could also be written like this, but then your reactant would look like this. And you're just trying to calculate delta G the way you have been for other reactions as well. If your solute is covalent, then you just have your solute in whatever original state it exists in. Could be liquid, could be solid, could be gas, and then it goes into an aqueous phase because covalent solutes don't break apart into ion. Okay. So what we want to do now is we want to do an example where we calculate the delta G of solution and use that as a way to predict whether a solution will form or not. So here I'm giving you three examples. Solutes. AgCl and CaCl2 both are ionic solutes, and then CO2 is a covalent solute. They're in different states, but we can calculate their delta G of solution. Remembering how we calculate delta G in general, there's a few ways we can do it. We can use delta G formation values. We can also use the delta G formula of delta H minus T delta S. And we're going to do both of them here, but we'll start with using the delta G of formation because that's the easier route, right? And so what I need is a series of these delta G formation values, which I can find from any thermodynamic table. The one that we used previously in the thermodynamic chapter would be just fine. What I've done is I've included all of those values here in this table, as you can see. So the delta G of formation values is on this column. And all I'm going to do is just calculate it for each of the solutes that I have when they form a solution. So I'm going to show the work here on the right. You can see that for the first reaction, it's just AgCl going into the aqueous form, which then splits apart into its ions. So I'm able to find the delta G formation value. So all I'm doing here is taking the delta G formation of silver multiplied by 1 mole, since the coefficient is 1. So that's why it's just 77.1. This is the delta G formation value for chloride ion, negative 131.3. And then minus the reactant, and the reactant is AgCl solid. So That's what its delta G of formation value is. And we ended up getting positive 55.6. And if you get a positive delta G, that tells you the process is non-spontaneous, which would tell us that this particular solute, AgCl, is not going to be soluble in water if we mix it at that given condition. Okay. Now I would highlight the importance of using delta G formation is that when you get these values of delta G formation, it is determined at a specific temperature, usually 298 Kelvin. So keep in mind that the value that we calculate here, that's positive 55.6, is for the reaction being done at 298 Kelvin or 25 degrees Celsius. This process might happen at some other temperature, which we'll investigate a little further later, but this is just something to keep in mind. Right now, all the conclusion is based on mixing the solute and the solvent at 298 Kelvin. I can do the same for the CO2 dissolution. Here I'm just taking the CO2 in the gas form and putting it into the CO2 in the aqueous form. Again, I have values of delta G formation here in this table, CO2 in the gas and then CO2 in aqueous. So I could use those to make my calculation. I get positive 8.4 kilojoules, which also tells me that CO2 is not going to be soluble in water at that condition, that temperature. Lastly, I'm going to try it with CaCl2. And in this case, slight difference here because I have a coefficient of 2. So you see that's why I'm multiplying that number by 2 because of the coefficient. If I calculate this one, I get negative 67.5 kilojoules, which tells me that CaCl2 is soluble in water at that condition. We don't really know what it is that is making this particular solution form or not form, right? So in order for us to investigate that further, we're going to need to use this second form of our delta G equation, which is the one where we break it apart into two components, which is our enthalpy factor and our entropy factor. Because we want to know, is it the enthalpy that is making the solution formation favorable, or is it the entropy, or is it both of them, or is it not neither one of them? Okay, so in order for me to do that, I already have the values of delta H of formation and the absolute entropy value here. I can just go ahead and calculate the delta H and delta S for each of those solutions, the three solutions that I showed you earlier, which is AgCl, CO2, and CaCl2. So if I actually break it down into the delta H of solution and delta S of solution, this is what I find. Again, I'm using the same exact formula, which is products minus reactants for each of those numbers. I find that for AgCl, the delta H of solution is very positive. So again, keeping in mind here that our main equation for delta G of solution is delta H of solution minus T delta S of solution. And for a spontaneous process, the delta G has to be negative, right? So my delta H is positive, which means it's unfavorable. My delta S is also positive, which is favorable. Remember, we want entropy to increase for the process to become spontaneous. So in this case, the reason why that particular solute is not dissolving is because it has a really unfavorable delta H. Delta H, as we'll talk about some more later, is a measure of the intermolecular interactions between your solute and your solvent and how much of it needs to be broken, how much of it needs to be reformed. So clearly that process in this case is not favorable. The delta S though is favorable. So that means that there is a point, because delta S is multiplied with temperature, there is a temperature value where this process could be made favorable. And in fact, as you see, I can make that whole number negative if I make this temperature number higher, okay? And so there is a point when AgCl will dissolve, and in fact, it will dissolve more and more as you make the temperature higher and higher. Okay, so this is clearly one of those salts where its solubility is temperature dependent. If you look at that gas, which is the CO2, it's kind of the opposite profile. Here you see that you have a favorable delta H of solution, right? It's a negative number, so that means that it's exothermic, so it's making good interactions with water when it's dissolved. The delta S of the solution, though, it's negative, which means that it's unfavorable, okay? And this makes sense, right? Because you're going from a gas state, which is the highest entropy state, right, into a solution state where now the gases are being surrounded by some water molecules, which is less ordered than the pure gas state. So the entropy decreases and it's unfavorable. So this is actually the opposite situation than the AgCl situation. Here, if you increase temperature, you actually make this solute dissolve less and less and less. So in fact, to make CO2 dissolve, you want to keep it at low temperature. And this actually fits with our experience of carbonated beverages, which contains dissolved CO2, because what you do is when you have these carbonated beverages, you keep them in the fridge because you want to keep that carbon dioxide dissolved in the solution, right? Because if you let it sit at warmer temperature, actually, and you leave it open, then the CO2 will escape and the soda will turn flat. The last component, which is CaCl2, is interesting because it actually has the same exact pattern like the CO2, exothermic, delta H, and then unfavorable entropy. However, in this case, the delta H is so exothermic, it's negative 81.6, it's pretty favorable. It's so favorable that it overcomes that delta S of solution. But if you keep increasing temperature, eventually this thing will also not dissolve anymore. So this is one of those funny examples of a salt that dissolves even less as you increase temperature. Okay, but because its delta H of solution is so negative that it makes that salt dissolve pretty well at a large range of temperature until you crank the temperature up so high that eventually it doesn't dissolve anymore. Now I want to draw some conclusion as a result of these calculations and what we just did here when we look at both the delta H and delta S solution. Generally speaking, when you have solid and liquid solutes, okay, the delta S of solution would be a positive number, right? In other words, delta S drives solution formation. And the reason, of course, is because solid and liquids are fairly ordered, structured, and then when you bring them into the solution form, now they're broken apart and they're being surrounded by water particles. And so generally speaking, that process increases entropy. Okay, so it makes the delta S positive. So if the delta S is positive, then we know that it's going to be favorable. Now, whether a solution actually forms or not really depends on the delta H at that point. Is the delta H favorable or unfavorable? And if it's unfavorable, is it a bigger factor than the entropy or not? Okay, and this is something we will discuss a lot more in the rest of this chapter. For gaseous solutes, as we just saw in that CO2 example, the delta S is unfavorable. And again, it makes sense because you're going from a gas to an aqueous state, the gas being a higher entropy state. So you're losing entropy in that case, which makes it an unfavorable situation. Sometimes the delta H would be able to compensate for that unfavorable situation. Sometimes it wouldn't. So it depends on the specific type of gas that we're looking at. And we'll look some more at that later on. And then lastly, what we can say is that delta S is typically pretty predictable in terms of how it affects solution formation. So when you're dealing with solids and liquids, the delta S of solution is favorable. When you're dealing with a gas, the delta of solution is unfavorable. So a lot of whether a solution forms or not really depends on the delta H of solution, okay? And delta H solution could be positive, could be negative, could be zero, and that depends on what kind of solvent and solute are we mixing together.